Welcome to the exercises for chapter 4. This chapter is focused on understanding limits. Limits are super important in calculus. In fact, it is no understatement to claim that pretty much all of calculus is just an application of limits. Okay, so quite important foundational material. Exercise 1, the goal of this exercise is to estimate, to find a numerical approximation of the two one-sided limits using Zeno's paradox. There are multiple paradoxes that Zeno has gifted humanity with. I described this earlier in the chapter, but basically the idea here, the analogy that I'm presenting, is that if you want to get to a particular point, a particular endpoint from a starting point, you have that distance, and then you have that distance, and then you have that distance. So as you approach a point, you're getting closer and closer and closer by cutting the distance by two, but you never actually reach that point because you're always just getting a little bit closer. You're always inching closer without ever actually getting to the destination. So that is the fun little analogy that I presented earlier in this chapter to help you understand the concept of limits. Now, I have a qualifier at the end of this exercise, which I'll say now in the beginning, which is this method here that I'm presenting, this algorithm, this is purely for fun. This is just for you to develop intuition with for what limits actually mean. The idea is you're considering what happens to a function as it gets closer and closer to a point. The algorithm that you are going to implement in this exercise is not actually a good way to compute limits in practice. This is great for education. It's great for improving your math coding skills, data visualization skills. But yeah, in practice, this is not a legit rigorous method. Okay, all of that aside, let's see. Here is the function. So you want to start this exercise by implementing this function here in NumPy. We'll get to SciPy in or SymPy in the next exercise. Here you want to implement this in NumPy and then create a graph that's going to look something like this. So here you see the plot goes from -2 to +2, and yeah, it's a pretty neat looking function here. Okay, so now for the algorithm to estimate the limit. So the idea is that we want to know the limit of this function as x approaches 1. That's what you see here. And you can see on the graph that's going to be, whatever that function value is, looks like it's 3.4 or something. So what we want to do is basically start from x equals 0 and then approach this point, x equals 1, closer and closer by taking the x-axis value and halving the distance. So we start at 0. So here is the x-axis value is 0. And this is the function value when x equals 0. So this is f of 0. And then we take half of the distance from 0, which is the current x value, to 1, which is our target limit value. So half of that, of course, is 0.5. And then we evaluate the function again. And then we have this distance, so the distance between this value and 1, that is 0.75. And then we get the function value and then have that distance, get the function value, and so on. You can see we're inching closer and closer to our target value of 1 without ever actually realizing the value of 1. So without actually getting to x equals 1, we're just getting closer and closer and closer. So that's the one-sided limit from the right. Then we have the one-sided limit from the left. The algorithm is exactly the same, except now we're starting from 2 instead of from 0. So here you can see we're getting closer and closer to 1, but going down instead of coming up. Okay, so that is the algorithm. And then you want to evaluate the function at exactly x equals 1, and then basically compare this to what the limit is suggesting. The final part of this exercise is to basically visualize this limit as it approaches a value of 1. So you can see here we start at 0, and here we get to half the distance to our target value of 1, and then half of that distance, half of that distance, and half of that distance. This will help illustrate the concept of limits and also help you understand Zeno's paradox, which is just an interesting kind of philosophical, physical, mathematical quandary to consider. Now, I haven't mentioned this specifically in the instructions, but to solve this problem, you definitely want to have a function, a Python function, to represent this mathematical function. I chose to do that with a lambda expression. You could also do that with a regular def-based Python function, but you definitely want a function instead of just evaluating this equation, because you want to be able to reevaluate this equation over and over again for lots of different values of x, or here I call this variable u inside the lambda expression, but that's just arbitrary. Okay, so this is the x-axis values for the plotting. So I can show you that code first. That's actually really straightforward. Once we have the function definition, then we just plot x by f of x. Okay, and that looks like this. This just reproduces the margin figure in the book. Okay, here is the key code for this exercise. So we start with defining our limit value, that is the limit as x goes to a, where a equals 1. And then I have the starting values. So, there's multiple correct ways you could solve this problem. I chose to do it by creating a NumPy array for the two x-axis values where we begin. So we're approaching from the left and from the right. We're calculating the two one-sided limits, or approximating the two one-sided limits with this little algorithm. And I chose to do this in a for loop, basically, where I vectorize the starting values. So these two values here, a minus 1, this is going to be 0, and this is going to be 2. And they're slowly going to get closer and closer to the target value of a, which is 1. Okay, 10 iterations, and here is where I run the algorithm. So I loop over the different iterations. I compute the function value at x sub naught here, x0, and then I update the x-axis values. Okay, so once we have this, we have the x and y values for this particular pair. Then what you want to do is update the x-axis value, here I call this x0, to be half the distance between its current value and the target value of a. And this is how I implement this. Okay, here is a little question for you. The question is, what would happen, if anything, if I just swap these two sets of code lines? So if I'm updating the x-axis values before calculating and storing the limit and the expression. So that is a question for you to ponder. It's also something you could test empirically. You can run through these results with and without, with the x-axis values being updated after versus before this line of code. Okay, so I'll run that. And then here I'm going to print it out. So this reproduces the text in the book. You can see it's just the x-axis values and the limit values. That's exactly what I calculated up here. And then basically I'm just combining these into one matrix. Now this is going to combine them into a matrix with two rows. And I think it looks a little bit nicer as two columns. So that's why I'm transposing it. So that's just my personal preference. I can show you what it looks like without this. Yeah, so I think this is just harder to look at. All right, and then we have the function value at exactly x equals a. And so the main point here is to see that the function value is very close to the limits as we are approaching from the left and from the right. Again, this algorithm here, this is like a fun analogy for understanding the concept of limits. This is not a formal, rigorous method for calculating limits that I discuss in the book. Nonetheless, if you would continue with this algorithm ad infinitum, you keep going forever, then eventually you would find that this value here, this function value here, is exactly equal to this function value here. Now, because this function is continuous at x equals 1, the limit actually does equal the function value at x equals 1. That is not guaranteed to happen for all functions and all points, all x-axis values. That happens here because the function has this special property of continuity at this point. So the plugin method actually is the limit. Okay, then the last part of this exercise is just to visualize. This actually isn't so difficult. So here I'm replotting the function, and then here I'm plotting the x-axis values by the limit values. Okay, and then, yeah, I think this is just really neat. Here's an optional zoom in, so you can uncomment this line of code, and that basically just zooms in the function. Instead of looking at this function from -2 to +2, we're going to zoom in a little bit to just the area where we have been focusing on. And you see, this is getting closer and closer. Maybe I'll even set this to like 0.1 and zero point 0.1. So the more we zoom in, the more you can see that we are approaching this limit value of x equals 1. We're getting closer and closer and closer. We never actually reach that exact x-axis value. That's the idea of a limit. You want to know, how does the function behave when you get arbitrarily, infinitesimally close to a particular x-axis value without actually touching that x-axis value. The goal of exercise 2 in chapter 4 is to explore calculating limits using SymPy. So instead of approximating limits empirically, numerically, as you did in the previous exercise, here we are going to use SymPy to get an exact analytic solution to the limits problem. Okay, so start by re-implementing the equation that we used in the previous exercise. It's reprinted here. But now you want to implement this in SymPy instead of in NumPy. It's actually very straightforward. You just copy paste the code and be sure to replace the NP for NumPy with SYM for SymPy. So we get a symbolic representation of this function. And then I want you to use LaTeX coding and print out in the Python notebook what you see here. So this function, this pair of lines, this is just the definition of the function. And here we see replacing or substituting the x for the value of 1 and then evaluating that. And what you see is that, well, you don't see any evaluated numbers, right? So SymPy is telling us that cosine squared of 1 is cosine squared of 1, and pi is just pi. If you would see a number here, like 3.14, etc., then that is not the real value of pi. That's just an approximation to some, reasonable degree of accuracy. Okay, so the point is that SymPy is giving us the analytic symbolic answer here. Okay, so then what you want to do is basically create a output in SymPy that looks like this. So we have the one-sided limit calculated with SymPy as x approaches 1 from the left and then from the right. And here you see two answers. So this is the output of SymPy. This is the symbolic limit as we approach 1 from the left. And what I have here in numbers, this is the result of evaluating this symbolic representation to, whatever degree of precision we trust SymPy to evaluate it to. Okay, so this is evaluated as a number. Here we have the one-sided limit as x approaches 1 from the right. And then we have the two-sided limit as x approaches 1. And then we have the function value at the exact limit value. And this was calculated in NumPy. In fact, to get this value, I just reused the function that I defined in the previous exercise in NumPy. This exercise is really good practice for improving your SymPy coding skills with LaTeX and limits and everything like that. Okay, so here I create a symbolic variable x, and then here I implement the function. Again, I've said this a bajillion times before, but just make sure when you're working with SymPy, you want to use the SymPy functions and not the NumPy function. Okay, here's the limit value again. And then here I'm just printing out what the function looks like converted into LaTeX. And here I'm substituting for x, I'm substituting a. Okay, so then we see basically exactly what I showed in the text. Here is how you calculate the limits in SymPy. So sim.limit, then you input the expression, the function, the value that you, the variable that you want to calculate the limit of, and that is, you'll see that come up later in the course when you get to multivariable limits. So if this were a function of more than one variable, then SymPy would need to know which variable we actually care about. So the expression, the variable, and then the actual value. And here, optionally, you can specify the direction for a one-sided limit. So the direction can be minus, meaning you're coming in from the left. It can be plus, meaning you're coming in from the right. Or you can say plus minus, meaning the two-sided limit. Now, actually, if you're calculating the two-sided limit, specifying the direction like that is not necessary. You can just leave it exactly like this, and SymPy will assume that you want the two-sided limit. So I'm showing this here for completeness. All right. Yeah. And then here, this is going to give us the symbolic representation. Here you can see this piece of code here is exactly the same as this piece of code here. I'm just wrapping it around sim.n, which is the numpy, sim.numpy. So this function here will transform this symbolic number into a floating point number in NumPy format. All right, so all of that, and then yeah, this is a function. This is a Python function that I defined in the previous exercise. And what you can see here is that all of these values are equal to each other, right? So the one-sided limit from the left equals the one-sided limit from the right, equals the two-sided limit, which also equals the function value. That is not the function value at exactly the limit point. That is not trivially guaranteed to happen. This happens because the function that I chose and also the point that we chose, so x equals 1, the function is continuous at that point. So we are going to see this kind of behavior. If the function has a discontinuity for any type of discontinuity, then these four numbers are not guaranteed to be equal to each other. The goal of exercise 3 in chapter 4 is to understand how SymPy deals with limits as we approach an infinity or an infinite discontinuity. Now, this is not calculating the limit as x goes to infinity or minus infinity. We'll deal with that some other time. What we are interested now is how SymPy deals with limits as we approach, as the function blows up to infinity or maybe minus infinity. Okay, so what you want to do is start by implementing this function as a SymPy expression, 1 over x minus 2 squared. And then you want to convert this SymPy expression into a Python function using sim.lambdafy, and then make a visualization that looks like this using matplotlib. Okay, so this is good exercise, good practice for your coding, and in particular, translating SymPy objects into NumPy and visualizing with matplotlib. Thereafter, what you want to do is compute three limits of this function as x goes to 2. You can already see that something weird is going to happen when x equals exactly 2. Actually, when x is exactly 2, we get 1 over 0. But as x gets closer and closer to 2, either from the left side or from the right side, then crazy, crazy things are going to start happening in this function, as you can see in this visualization. Okay, so you want to compute in SymPy the limit as x goes to 2 from the left, the limit as x goes to 2 from the right, and the two-sided limit as x goes to 2. Now, the answer, as I printed here, looks like SymPy is telling us oo, but this is oo, so you can't pronounce it as oo. But basically, this is how SymPy prints out infinity in ASCII text. Here we have our function definition, and actually notice that I'm not defining x up here to be a symbolic variable x. So if you have used the variable x earlier, before running through this code, perhaps as a NumPy array or as a regular floating point variable, for example, you might get an error message or you might just get some incorrect result here. So just be mindful of that, these variables getting floating around and sometimes needing to be redefined. Okay, anyway, so here is the function as a SymPy expression. Here I lambdafy it. Remember, when you're using sim.lambdafy, the first input is the symbolic variable, and then we have the name of the expression that you want to lambdafy or convert into a function, a regular Python function. Okay, and then here's where I'm doing the visualization. Nothing super interesting going on here. Certainly nothing you haven't seen before elsewhere earlier in this code. Okay, and here we get a warning message. This is not an error, it's a warning that we have a division by 0. And of course, you know why that happens. That happens because we go from 0 to 4 in 1,001 steps. So there is an exact value of 2. Now, here's a question for you to explore. What happens to this warning message when you change this number of points between 0 and 4 when you make that be 1,000 instead of 1,001? So I will leave that as an exercise for you to explore. Okay, and then here, well, you've already seen how to compute the limit in SymPy using sim.limit. Again, you write in the name of the expression, the symbolic function, the variable that you want to compute the limit relative to, the value that we are approaching, and the this optional input dir is for the direction. So whether we're computing the one-sided limit coming from the left, the one-sided limit coming from the right, or the two-sided limit. And also, as I've mentioned before, the two-sided limit is the default option. So in fact, you don't need to list it explicitly. I just wrote it in here for clarity. Okay. And then we get in all three of these cases, the limit as x approaches 2 is infinity. And obviously that makes sense from the graph. Thus far, we have explored using SymPy to calculate limits at points where a function is continuous. We have explored using SymPy to calculate limits where there is an infinite discontinuity. And now we are going to continue to explore how SymPy calculates and reports limits with at points where there are discontinuities. But in this case, it is a jump discontinuity. Okay, so here's what you want to do. Implement this fraction, this function here in SymPy. So the absolute value of x minus 2 divided by x minus 2. So implement that. Now, I don't explicitly state in this exercise to make a visualization, to make a graph of this function, but it's always a good idea to do that. So I definitely recommend getting into the habit of visualizing anything and everything you can possibly think of in order to gain a better intuition for function behavior. And in particular, if you're asking questions about certain points of a function like a limit, it's really great to have a visualization, even if you are not specifically required to make a visualization. Okay, so from here, basically it's similar to what we did in the previous exercise in that you want to calculate in SymPy 3 limits. So the limit as x goes to 2 from the left, the limit as x goes to 2 from the right. So those are the two one-sided limits. And then we have the two-sided limit. Okay. And I don't tell you what happens. I want you to discover it for yourself in SymPy. Here I define the function. Remember that in SymPy, the function for the absolute value is capital A for who knows what reason. Now, anyway, here I'm just making a quick and dirty, very simple plot with sim.plot. If you decided to make this plot in matplotlib by converting this into a NumPy array, evaluating it for different values of x, and using matplotlib, that's great. Totally fine. Great skill to have. And the more experience in coding that kind of stuff you can get, then that's really great. However, I just decided that that a kind of quick and dirty graph is good enough for me. So anyway, here's what the function looks like. It's -1 where x is less than 2, and it's greater than, it equals 1 when x is greater than 2. And when x is exactly 2, then we have 0 over 0. So the function is undefined at that point. Now, what is the limits here? Before, I'll show you the SymPy code in a moment. But we should be able to understand the limits of this function as x approaches 2, partly from looking at the graph and partly from looking at the function. So we know we can determine that the limit as x approaches 2 from the left is -1 when x approaches 2 from the right. It is +1 and the two-sided limit as x approaches 2 does not exist. It doesn't exist because the two one-sided limits are different from each other. And of course, the value at exactly x equals 2 is undefined. Okay, so let's see what happens. I think I'll actually print these things out one at a time. So from the left, we see that the limit is -1. And now from the right, we see the limit is 1. So far, so good. Let's see what happens when we get to the two-sided limit. Now here, this is pretty interesting. We get an error message, and the error message tells us that the limit does not exist since the left hand and the right hand limits are not equal to each other. Great. This is a very nice, beautiful error message because it's highly informative. It tells us exactly what the problem is. Now, it turns out that this error message really happened when we tried to convert to a string. So let's see what happens when we just, let me see, I'll comment this out. So just running this function in particular is not the thing that gives us an error. You can see that the function runs fine. It gives us a, here I'm just storing it. The result is an output variable. And that variable is, well, it doesn't really tell us much. It just tells us the limit. It's just giving us back the nature of the problem, although it decided to determine that it's best to calculate this from the right side. Okay, so now if we want to actually see what this is, sometimes I write eval f to evaluate the function at a particular value. And it turns out in this particular case, when we have a limit object that is not fully defined as a finite number, then, well, we still just get the same thing back. So another method you can try in SymPy is called do it. So you're asking SymPy like, hey, I get the symbolic representation. I want to see a number. Just do it. Right? And so here the answer is 1. And again, the answer is 1, not because this is the two-sided limit, but because this is, because SymPy just gave us the one-sided limit coming from the right. Now, why the SymPy developers chose to implement it that way, I cannot say. I actually much prefer this approach, where, when we're trying to convert to a string and trying to print out the message there, we get an highly informative error message. I think this would be also appropriate behavior to act here. In this chapter, I described 4 important properties of limits. These 4 properties are used a lot in developing proofs of differentiation rules and integration and lots of other things in math. So the goal of this and the next several exercises is to demonstrate, to design case studies to illustrate these properties. Okay, so in particular, in this exercise, exercise 5, you are going to demonstrate one property, which is the factorization. So in particular, that is the idea that the limit of a scalar times a function is exactly the same as that scalar times the limit of the function. In other words, if you have a scalar multiple of a function, you can pull out that scalar and then calculate the limit without that scalar, and then multiply whatever the resulting limit happens to be by that scalar. Okay, I hope that makes sense. What you want to do in particular is implement this function as a SymPy expression, so as a SymPy variable, using symbolic variable x. And then you can make a quick and dirty plot that looks something like this. I used sim.plot to make this visualization. If you want to use matplotlib, that's great. Go for it. You can change the colors. You can make the graph look nicer. Okay, but the key part here is that you want to come up with some scalar. Maybe it's the number 4. Maybe it's the number minus 27.3 bajillion. I don't know. What I chose to do was come up with a random scalar, gamma, so that every time I rerun the code, this scalar actually ends up being a different number. Okay, and then you want to compute basically what you see here. So the limit of the scalar times the function, and then the scalar times the limit of the function without the scalar, right? So the scalar is either inside the function multiplied by the function, or we first calculate the limit of this function, as x goes to 5, and then multiply whatever result that ends up being by the random scalar. Now, it doesn't actually matter what the limit value is. In this exercise, we do not care about the limit value per se. What we care about is that these two numbers are the same as each other. So these two should match. Every time you rerun my code, because I have a random constant, these numbers are always going to be the same. When I switch to Python in a moment, we're not going to get minus 534. But every time, this answer and this answer will be the same, almost exactly the same. You can see the very, very, limits of computer precision here. We got a tiny, tiny difference. That's fine. So here I implement the function, the mathematical function, as a SymPy object. Again, I'm using a symbolic variable x, which I do not explicitly define here because I've defined it earlier in the code. So you might actually need to include a redefinition of the symbolic variable x. Okay, here is my plot in SymPy. There's a little bit of extra things I included in here because I want to save it as a PNG for publishing the book. Okay, and then I print out the function as you see here. Okay, and now you can see here I'm generating a random constant. Here I calculate the constant times the function, and then the limit of that. And then sim.n, as you know, is converting into NumPy, is basically just making sure that we're getting a floating point number out of this and not a symbolic representation. Okay, and then here, this code looks really similar to this, but they are not the same. Here, I'm calculating the limit of the function, not the function times the scalar. And then, after calculating the limit, that is when I multiply by the scalar. Okay, and again, yeah, the number is going to be different every time I run the code. The point is that this number and this number are the same. This is a demonstration of the scalar multiplication property or the factorization property of limits. Now in exercise 6, we are going to explore the additive property of limits using SymPy. So here is the additive property of limits. If f and g are two functions of x, then the limit of f plus g equals the limit of f, and then separately calculated the limit of g, and then the sum of those two limits together. Okay, so use these two functions. So you need to implement these two functions in SymPy, and then you can choose a value at which to evaluate these limits. So I chose the limit of these two functions as x goes to pi. You can choose some other variable if you like. It's totally fine. You have to be mindful of domain restrictions. For example, you don't want to calculate the limit as x goes to minus a billion because that's just not possible with this function. And then you want to calculate two limits in two separate lines of code. The limit of the function f plus the function g as x goes to pi or whatever number you pick, and then separately calculate the limit of f and the limit of g, and then add those two limits together. Again, it's important to make sure that you're using the same limit value, right? If you calculate the limit as f or of f as x goes to 2 plus the limit of g as x goes to 4, obviously these two numbers are not going to equal each other. One of the reasons why I chose to use pi as a limit value for this exercise is to see what happens when we compare using numpy.pi, which is a number. This is not actually the symbol pi. This is just, pi calculated out to 16 numbers after the decimal point or whatever, versus sim.pi, which actually is the symbolic representation of pi. Okay, so here I have the two functions, the log of x plus x squared and e to the minus x plus x cubed. And again, as always, make sure you're using the SymPy version of these functions and not the NumPy version of these functions. Okay, and then here you can see I'm adding these two functions together and computing one limit. here you can see I'm calculating two limits separately from each other, each one for one of the functions, and then I add the results. Okay, and yeah, it doesn't really matter what the number is, although it's interesting that it ends up being 42. I swear that was not planned, it just happened to work out that way. But the important thing is that these two answers are the same. These two numbers are the same as each other. As I mentioned in the book, that's a really nice demonstration. This helps you build intuition. It helps you build coding skills and math skills. This doesn't prove rigorously the addition property of limits. I discuss in the book how to prove that. I'd show a proof for that. But this is a really great demonstration. It's an illustration of this property. Okay, so now, yeah, I'm just going to try it again using sim.py instead of numpy.py. Oops. And then let's see what happens here. Here, this is pretty interesting. SymPy now recognizes that this is the symbol pi and not the number pi. So in fact, we just get the symbolic representation of the limit instead of a numerical result. So we can use eval_f, and that's going to give us a numerical evaluation of this symbolic expression to, some ridiculous degree of precision. And you can see that this number matches this number. Now for the multiplicative property of limits in SymPy here in exercise 7. This exercise is really, really similar to the previous exercise. In fact, you should use the same two functions as in the previous exercise. That's where we explored the addition property of limits. But now instead of adding these functions together, we are going to multiply these functions together. So again, the idea is to calculate two sets of limits. On this line, you first multiply these two functions and then calculate the limit. And I chose to use the limit as x approaches pi. You can choose any other number, it's fine. And then here in the second line, you calculate the limit of f separately. We have nothing to do with g. And here the limit of g separately have nothing to do with f, but of course using the same limit value, and then multiply those two limits together. Again, as I mentioned in the previous video, the numerical answer here doesn't matter. What matters is that we get the same result in both approaches. And this is an illustration of the multiplicative property of limits. Once you've done this part, then also just something small and interesting to do is to compare the limit of f cubed, so the function value cubed. Now, that means like you take the function and you multiply it by itself, and then you multiply it by itself again. So the function itself cubed with the limit of f of x as x approaches pi once, and then multiply it again, and then multiply it again. Again, these should be the same. Okay, very straightforward. In fact, I just copied and modified this code from the previous exercise. So here we are multiplying the two functions together and calculating one limit. Here we are calculating the limit of one function multiplied by the limit of the other function. And no surprise, we see that those limit values are the same, demonstrating the multiplicative property of limits. Okay, and then here for powers, but this is really no different from multiplication, but instead of multiplying two distinct functions, I'm multiplying the same function, and now 3 times instead of 2 times. So the only possible way you could go wrong here is if you make like a silly little typo somewhere. And then, yeah, the fact that we get these two numbers being identical to each other is a demonstration of the multiplicative property. And now to conclude this little mini set of exercises on the properties of limits, we have exercise 8, where you are going to explore and confirm the divisive property of limits. So really, really similar to the previous couple of exercises. In fact, the same functions from exercise 6, but now instead of adding the functions, instead of multiplying the functions, you are going to divide the functions. So the limit of f divided by g equals the limit of f divided by the limit of g. Now, as I mentioned in the book, this is one limit property that you have to be a little bit mindful of. because it is possible that the limit uh, of g of x as x approaches some number is 0. And if that is the case, then you're dividing by 0, and then this property actually no longer holds just because of this division by 0. Other than that exception, this property holds. And in fact, it's quite useful. You're going to use it later in the book. Okay, so this is confirmation that the divisive property works. And then to explore where something weird might or might not happen, you can create a new function, h of x, which is this. So it's x cubed plus x squared plus x, and then print out the limit as x goes to 0 of g of x. Now, g of x is the same as what we've been working with above. So e to the minus x plus x cubed. So let's see. Yeah, so print out the limit as x goes to 0 of g, the limit as x goes to 0 of h, and then the limit of as x goes to 0 of g divided by h. And then let's see what happens. Well, this code is starting to look familiar to you by now. This is basically the same exact code that I've now copied and pasted multiple times, 3 times from the past several exercises. So one limit of the function divided by the other function, and then 2 separate limits for each function individually. And now here I'm just dividing them. And yeah, we get the same answer in both cases. Okay, so now we have a new function, h of x, and here is the definition of h of x. Here, let's see, I'm going to do this first like this. So this is the limit as x goes to 0 of the 2 functions individually. And here we see that it is 1 and 0. And now when we divide by these functions, something strange is going to happen. We get infinity. And why do we get that value? Well, first of all, let's just show that it's still a valid function. So there's nothing wrong with this function. It's not like a weird function. We just defined one function as the ratio of 2 other functions. Now, I would like you to spend a little bit of time trying to understand why we get this result here of limit going to infinity. I'm giving you one hint here, which is to calculate. Actually, I'm not even going to show this. I want you to do this on your own. So you can factor this function here, this ratio of functions here, and you could also plot the function and see what happens as the function, or what happens to the behavior of the function as x gets closer to 0. So that is something for you to explore using tools that you are now very familiar with from this chapter. SymPy is a great and powerful library for doing symbolic calculations in mathematics. We are going to use SymPy a lot throughout this book and all the exercises in the book. And it's pretty likely, if you continue working with applied math or using Python as a tool to learn math, it's likely that you will continue using SymPy. That said, SymPy is not perfect. It does not get everything exactly right in the sense of coming up with a correct solution that you would come up with or like an expert mathematician would come up with. I am going to highlight various sort of trouble cases in SymPy throughout this book. You've already seen a few, and the goal of this exercise, exercise 9, is to explore another one of these issues where SymPy seems to struggle, in this case with limits problems. So here's what you want to do. Implement this piecewise function in SymPy and make a visualization of this plot. So we've actually worked with this piecewise function before. It is basically a sine function for negative x. It is a quadratic for positive x. And when x is exactly equal to 0, then the function takes on a value of 1.5. So we have a jump discontinuity here. Then make a quick visualization of this function using sim.plot. Here looks like this. I've also discussed this in earlier exercise videos as well as earlier in the text of the chapter. That these lines here, so this function is mostly correct, but these vertical lines here are misleading because they suggest values that the function takes on, which is not really the case. So the function goes from here, from a value of 0 at 0, jumps up to 1.5 with no values in between. And then it jumps down to -4, also with no values in between. Okay, Let's see. Now for the test. Okay, so what you want to do is compute and print the two one-sided limits and the two-sided limits of this function as x approaches 0. Now, just from looking at the function and also considering the definition of the function, we can already determine what these three limits are. So as x approaches from the left, we have a value of 0, a limit of 0. When x approaches 0 from the right, then we have a limit of -4, and because the left-sided limit and the right-sided limit at x equals 0 are different from each other, this function actually does not have a two-sided limit. But SymPy actually calculates and prints out a two-sided limit here of 3/2 or 1.5. So this is incorrect. It's inconsistent with the definition of the function and the way that we know limits work in mathematics. Okay, and then the last part of this is basically just to confirm that SymPy really is representing this function correctly. So what you want to do is basically add a tiny, tiny little number to f of a, where a is the limit value, so x equals 0. So calculate the value of the function at just a tiny, tiny little bit below f of 0 and a tiny, tiny little bit above f of 0. And to do this, you can specify a tiny number to be EPS. So numpy.finfo float.eps. So this is estimating or telling you about the machine epsilon. That's what the EPS stands for, which is basically the smallest, the interval between the smallest interval between two numbers that your computer is confident in representing. So it's basically just a tiny, tiny number. Depending on your computer, blah, 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 the operating system, it's going to be somewhere around 10 to the minus 16. Okay, and then, well, I will discuss these results when I show you the solution in Python. Here I define the piecewise function at this point in the book, and certainly at this point in the exercises. There's nothing should be surprising here, right? Just make sure that you are specifying x exactly equals to 0 using sim.eq for equal instead of just writing x and then a double equal sign. Okay, so then, yeah, then we have a quick and dirty plot over here like this. Okay. Now for the limits values. Again, there's nothing new in this code here. You have seen this before. I guess the only, thing to remark here is that I'm converting this result from a symbolic answer into a NumPy representation, so into a floating point number. And that's why we get 1.5 here versus 3/2 over here. Okay, so again, we know that this is an incorrect answer because it should be that the two-sided limit actually does not exist. Okay, so and now here is the confirmation of SymPy accurately encoding this function. So let's see, actually I'll show you this first. So numpy.finfo and then float because we're looking for the EPS, the epsilon, the machine precision of a floating point number. And then that's going to be, 10 to the minus 16 approximately. Okay, so basically what I'm doing is substituting into this function where we see variable x, I'm substituting in the value of a, which is our limit value, and that we set to 0, a minus EPS, and a plus EPS. Okay, and then, this is going to confirm that SymPy is representing these numbers accurately. So this is sine of, some fraction, but look how huge this is compared to the numerator, which is 3. So this is basically 0. And of course, the sign of 0 is 0. So this is 0 plus a tiny, tiny, tiny little number. The function value at exactly the limit is 1.5 as we specified. And the function value just a tiny, tiny bit right of the limit is -4. Technically, it's going to be like minus 3.9999999. But this little number here that we're adding is so tiny that the function is still basically -4. You'd have to have a lot more precision here to see that it's actually a number very, very slightly larger than -4. So the overall conclusion of this exercise and also other demonstrations of difficulties in SymPy is that SymPy is really powerful. It's great. I recommend using it, but you should not just blindly trust everything that SymPy is going to output, especially these more kind of difficult cases. You really need to verify what SymPy tells you with your expert knowledge of calculus. The goal of this exercise, exercise 10, is to explore how SymPy deals with oscillating discontinuities. Remember from earlier in this chapter that an oscillating discontinuity is where a function continues to oscillate between some values or within some range, some numerical range. You often see this kind of behavior with trig functions like the sine of something or the cosine of some other, potentially nonlinear function inside the trig function. And now the idea, which you see visualized here, is that as we approach zero, then x equals zero, there is no real limit to this function because the function continues oscillating indefinitely, and the frequency or the speed of the oscillation gets faster and faster infinitely as we get closer and closer to x equals zero. In other words, there is no limit because the function does not settle onto any one particular value. Okay, so implement this function in SymPy. F of x is the sine of 1 over x. Create a plot that looks something like this in SymPy, and then again, calculate the limits of this function as x approaches 0 from the left, from the right, and the two-sided limits. Okay, and I'm going to talk more about what this output means and how to interpret it when I show the code. Here I define the function and generate a SymPy plot. Again, if you chose to do this by, or visualize this by translating this into NumPy and then plotting in Matplotlib, that's great. I support that 100%. But right now, all I want is a quick visual confirmation of how this function behaves. And so for that, I think SymPy is more than sufficient. Now, it looks like this function is just turning into a big, ugly black mess here as x goes towards 0. But really, the issue here is just all of the lines are being drawn on top of each other. This sine wave is starting to oscillate so fast that all the lines basically just overlap, and it looks like a big mush here. All right, let's check out the limits. This code should look familiar. It's exactly the same code as for the previous exercises, just copied and pasted. So as x approaches 0 from the left, from the right, and the two-sided limits. So now here we do not get a particular number. We don't get a specific number or finite number from SymPy. We also don't get any warning messages or error messages. Instead, we get this result that says accum bounds. This is accumulated bounds. So basically, SymPy is telling us that there is no limit. The limit is just the accumulation of numbers between the bounds of -1 and +1. Of course, those bounds make sense because that is the range of the sine function. And to confirm that that maps onto the sine function, what I encourage you to do is scale this whole function up by a little bit. So maybe scale this up by 3. So now we have 3 times the sine of 1 over x. I'm not going to do this here because I want to leave it as a little exercise for you to do. And basically the question is, when you scale this function by some scalar, what happens to the plot? And also what happens to the limits in terms of the bounds of this accumulation of numerical values? Welcome to exercise 11 of chapter 4. Here we are going to continue exploring limits using SymPy and also explore the multiplicative property of limits. So here is an interesting looking function. And the first part of this exercise is to implement this function in SymPy and then make a visualization that looks something like this. Now, before switching to SymPy, before switching to code, if you read the rest of the instructions, you will see that it actually makes sense not to implement this function as one line, but instead as 4 separate terms, and then combine them together. And the reason for that is that later on in this exercise, you are going to calculate the limit using SymPy of each of these terms individually. Okay, so I will get back to that in a moment. I'll do a little bit of switching back and forth between the book and the Python code. So for now, I'm going to switch to Python, implement this function, and create this graph. And we'll talk about that a little bit. And then I'll come back to the book to explain the rest of this exercise. So you can see that here I have created this function by first specifying all of the individual terms in the function, the 4 different parts of this function in a Python list. And now I'm just looping through all of these parts and building up this expression one piece at a time. So I implement or initialize this expression to be just the number 1. And then I say the expression equals itself times each of these parts. Okay, and then print this out, run that code, and print this out. And now here we see the entire expression. Here's some quick and dirty plotting in SymPy. Again, you can do this in Matplotlib. That's great. Now we are going to consider the limit of this function as theta goes to 0. Now you can already look through this function and see, what happens if we try the plugin method. What happens for 0 here? No problem. 0 here, no problem. Here we get 0 squared. Here we get e to the 0 squared, which is 1. And then here we have the sign of 0, also no problem to calculate. Here's where we run into problems. So theta squared, so 0 squared, we cannot take the log of 0 that is not defined. So basically what we see is that the domain of this function is all real valued values of theta except for theta equals 0. Now this function can also take negative values. The logarithm itself cannot take negative values, but into the log function, we are feeding theta squared. So when theta is negative, it's totally fine. We can still take the log of negative values of theta. Okay, and here's what this plot looks like. I think it looks pretty interesting. And now, the question is what happens to the limit? What is the limit value as theta goes to 0? Well, we can intuit an answer in 2 ways. One, we can try the plugin method and just look at the different terms. Basically, we have the product of 4 terms, and this term right here is going to equal exactly 0 when theta equals 0. So anything else times 0 is going to be 0. So just by looking at the mathematical formula, we can already kind of have a guess that the limit is going to be 0 because 0 is going to multiply whatever these other terms are. And then you also see that in the graph. Again, this is not a rigorous approach for exactly determining a limit value, but certainly the graph is consistent with the hypothesis that the limit of this function as theta goes to 0 is going to be 0. So that brings me to the next 2 parts of this exercise. One is to calculate the limit in SymPy as theta goes to 0, and also confirming that the function itself is undefined at theta equals 0. And then, okay, so that together was one part, and then here's another part is about the domain of this function. Now, I've already discussed the domain of the function. It's all real valued values of theta except for theta equals 0. So what you want to do here is basically just confirm this in SymPy using methods to calculate the domain of a function that I introduced in chapter 3. I forget which exercise it is offhand, and this is a double question mark here because I've only compiled this one chapter here, so it's missing this reference. So here is the value of the function at theta exactly equals 0, and here I'm reporting the limit of the function as theta approaches 0 from both sides, so the two-sided limit. So here we see that the function value is nan, not a number. It does not exist. And that's really because of that log term. And then we see that the limit is 0 as theta approaches 0, consistent with what we inferred from looking at the equation and also from looking at the graph. Okay, and then here is the function in SymPy to calculate the domain of a function. So we want this expression for variable theta, and we want to consider all of the real valued numbers. Okay, and then we see that the domain is from minus infinity to 0 with union 0 to plus infinity. And then we have the open parentheses here around 0 indicating that the exact value of 0 needs to be excluded from this domain. And this brings me to the final part of this exercise, which is just to confirm the multiplicative property of limits using this function. So what you want to do here is calculate the limit as theta goes to 0 of each of the four components of this function, each of the four terms that multiply together to produce this function. And then the multiplicative property of limits states that the product of all of these limits is equal to the product of the limit of the entire function. Okay, and now we see the problem here because we have a infinite number. So then the final part of this exercise is to repeat this part here to print out these calculations again, but using any other numerical value for the function. So for calculating the limit, where we expect a valid number. So I suggest using theta equals 1. You can use any other number. It doesn't matter as long as it's going to produce a finite limit. And that's what we see here. So this is the variable I'm using. Sometimes in other exercises, I just call this a, variable a, but here I'm calling this limit location. This is the value of theta that we are computing the limit at. Okay, then again, I'm looping over all of these parts. And here, printing out something, I'll talk about that in a moment. But basically here, I'm just collecting all of the limits as a product. So the limits product starts off, I initialize it as 1. And then I'm saying this variable limits products equals itself times the limit of this particular part. Again, for this variable and for this theta value. Okay, and then, this line is basically just printing out the limit location and the limit value. I guess, I'm now calculating the limit twice. This is identical code here that I'm using twice in the for loop. So I suppose it does make more sense to create a separate variable inside this for loop, specifically for this limit here, this function here, this one here, because I'm using it twice. But anyway, that's just a little tidbit about coding. Okay, so now we see the limit of theta squared as theta goes to 0 is 0. The limit of e to the minus 0 squared is, we can plug in to have e to the 0 equals 1. Sine, we can plug in and get 0. And here's where we get not a number. So Senpai is telling us that it's minus infinity, which is basically because as theta approaches 0, it's getting smaller and smaller. And so the log is plummeting down to minus infinity. Okay, so then again, we can try this with, how about the number 2? Because I specified 1 in the book, so now I'll use 2 here. Okay, and basically the point here is that this value here, the product of all the limits, is going to be some number, whatever this number ends up being. And that's the product of all of these limits, and that is going to be the same as the value, let me see the value here. So now instead of the limit as we go to 0, it's the limit as we go to 2. And well, this is not nicely LaTeX formatted, but actually maybe I'll do that. So this is going to say sim.latex. And let's see how this looks. And you can confirm that this number here is the same as the product of all of the limits of the individual terms that comprise this function. This is the multiplicative property of limits. Exercise 12 of chapter 4 is focused on using SymPy to double check my work in the limits expressions below. So basically here you see 5 different trig expressions and their limits as theta goes to different values, either 0 or looks like this one is to infinity. And here I have the answers written out. So the question is, are my answers correct? So what I want you to do with this exercise is pretty straightforward, actually. You just implement all of these expressions in SymPy, calculate the limits, and report them, print them out, and just see if I've made any mistakes. Maybe I've made a few typos. what I recommend doing to give yourself a little bit of an extra coding challenge here is to write the code for this exercise de novo. That means new, fresh, without looking back or copying and pasting any code. So just a little bit of a extra challenge to see if you can write all the code for this exercise completely from scratch without looking back at any other code from earlier in the chapter. As is very often the case, there are many ways that you can correctly solve this exercise. The way that I chose to do this was to write out all the functions in a Python list. So here I have a list that I call it variable function list, and there are 5 elements in this list. Each row here corresponds to a different element of the list. And then you can see that each element of this list itself is a 2-element list where I write the function using SymPy and the limit value to calculate. So then here in this for loop, I'm just looping over the rows in this, the elements in this list. It's a row. I think of it as rows because of the way I typed it out here. And then I'm just reporting the function and the limit value. And then here I calculate the limit in SymPy. Okay, and then we can print this out and look at it. I'm not going to go back and forth with the text, but basically it was the sine of theta over theta. It was this one, yeah. So this one here in the book, I accidentally wrote this as a 0. So all the rest of these are correct. I wrote it correctly in the book, but the limit of sine of theta over theta as theta goes to 0 is 1. That's something that I discussed earlier in this chapter.